Good afternoon to all of you. I hope you all can hear me and see my screen clearly. Good afternoon, Abhinav. Let's start with this class today. Today's class, we are going to talk about speakers further. We have already spoken about speakers, their basic design considerations. One popular type of speaker, that is a dynamic loudspeaker, and its components. We have talked about baffles, mounting, etc. in a speaker. Today we are going to talk about the horn speakers, multi-speaker system, efficiency of loudspeakers, loudspeaker distortion, and some problems. You might need your pen and paper, so please get it in the meantime. Going ahead, first to the horn speakers. So a horn speaker is slightly modified design of dynamic speaker. Of course, you need a diaphragm. You need more or less things. Uh, you more or less need same things. Just that the diaphragm is then connected to a horn-shaped design. Typically, here a horn means a conical structure. That conical structure transforms high pressure at the throat of the cone to a low pressure distributed over the large mouth of the horn. So it's here I can show you a design. This is my design. So you have this coil here, you have this diaphragm here. All these things are same. But you can see that there is a cone which is connected to it. This kind of loudspeaker designs were fairly common, and in fact you have seen it at many places. They were very economical, ready to move. You can hold them in the hand and speak. They're a step down transformer. Here the high pressure goes in a low pressure here. Just like in a transformer, high voltage goes into a low voltage. This is basically, these speakers were highly directional. So on this side, the sound output is very high. But if you go on to this side and this side, then the sound output really reduces. A little broader version of this is over here, which is typically referred as a folded horn. This is horn, and this is the folded horn speakers. I have a video to share you to the use of the folded horn speaker. You can see that here George W. Bush speaking from the site of 9/11 Ground Zero when the event had happened, and when he has visited the site for the first time. So let's have a check.
I want you all to know that America today is on bended knee in prayer for the people whose lives were lost here, for the workers who work here, for the families who mourn. This nation stands with the good people of New York City and New Jersey and Connecticut. With the good people of New York City who mourn.
Please check the drop in the sound intensity when he turns uh, uh, from facing camera to facing on the other side. You will find that the sound intensity drops drastically. That's how directional the speaker is.
For the workers who work here, for the families who mourn. This nation stands with the good people of New York City and New Jersey and Connecticut as we mourn the loss of thousands of our citizens. I can hear you. I can hear you. The rest of the world hears you. And the people who knock these buildings down will hear all of us soon. The nation sends its love and compassion to everybody who is here. Thank you for your hard work. Thank you for making the nation proud. And may God bless America.
So that's a horn speaker used for a very small gathering, highly directional, but very flexible in using. Let's go to the next idea, and that is multi-speaker system. In the beginning of the chapter, we had put forward the idea that you cannot design a single speaker system which can reproduce the entire frequency band faithfully. Practically, if this if the speaker is small in size, it might be achievable. For example, the headphones, earphone speakers, they do achieve entire spectrum range because the volume of the air to be moved is very small. However, if you are going to a large room, big speaker, if you want larger volumes, then a single speaker delivering the entire frequency spectrum is not feasible. So we require a multi-speaker system. So today we will talk about the basics of multi-speaker systems. So this is how they look like. In fact, mostly the chances that if you have any decent speaker at your home, it would be a multi-speaker system. Typically, a multi-speaker system is at least having two speakers. Uh, One typically a large speaker, which is a low frequency speaker, and one small speaker, which is normally referred as tweeter, which is a high frequency speaker. So these two together combine what is called as a multi speaker system. In some of the advanced designs, you get three speaker here also. The woofer, which is a large cone, this bigger one is called woofer, which has a large cone at low frequency, while this is a large coil. It has a large coil, it has a deeper cone and soft suspension. It's a very soft suspension, it moves very smoothly. Now the tweeter, which has a small high frequency, tweeters are very small and they have very high frequency, and they are highly directional. On contrary, woofer is very smooth and moves very woofer is very multi-directional, low frequency. Small, lightweight, this is about the tweeter. This is a small, lightweight coil, but it has a stiffer suspension. Horn or dome radiators also form in some of the speakers. So this particular section becomes a horn kind of thing, which I had talked earlier. Sometimes in a high range speaker system, you get a middle speaker as well. Now, we do achieve this design by using what is called electrical crossover. Now, an electrical crossover is nothing but you can achieve it by using a simple low pass filter or a high pass filter design. So, what is a low pass filter or a high pass filter design? So, you are quite familiar with it. A low pass filter, high pass filter, you have designed using capacitors and resistors in series in the electronics course. So you can use one such simple electronics design, and so as I said, woofers, they take lower frequencies, so you can have a frequency response that is being fed to the woofer in this manner, and you can have the frequency response which is fed to the tweeter in this manner. So you can apply a cutoff somewhere in such a way that the cutoff point is common to both. Okay, so the high frequency output, like when the frequency is produced, for example, when a music is produced, the high frequency will automatically go to the tweeter, while the low frequency would be fed to the woofer. Band pass filter for mid-range speakers. As I said, some advanced speaker system use three. So you use a band pass filter. So for tweeter this way, very low frequency goes to woofer this way, and the mid-range frequencies here will go to the mid-range speaker. So this is some of the expensive speaker systems employ. Extra large subwoofer for very low frequency. So in some cases, the woofers are designed separate. Like if you go to a big concert or in a big hall, then sometimes a woofer is bought and arranged separately that actually can generate frequencies up to very low frequency. It deals exclusively a frequency between 20 hertz and 80 hertz. So that is another component sometimes. So that's how a multi-speaker system will work, taking the common signal using filters. It can send it to the different speakers. I'm going to talk about this in a little while. That's how it is achieved in the modern day system. This was all designed in 60s and 70s and 80s, and those days you had mechanical buttons on the or sliders on the system in which you can either increase the gain of any section, tweeter, mid-range or woofer. You can increase or decrease the gain, and you can change the composition of the music output. This was being done earlier, long back, up to 70s, 80s, 90s, and after that the software took over. So I'm going to talk about that towards the end in today's class. These kind of speaker system, they are designed in a way that they can be kept anywhere. We'll talk more about it in a minute. So this is how typically a drawing or design would look like. This is your input. You use a low pass filter here. An inductor is shown over here as a low pass filter. At higher frequencies, you know the impedance of the inductor shoots up. So current here will reduce. So high frequencies will not go to woofer, but the low frequencies, the current will pass through the woofer, giving you the sound output. Now a parallel connection is fed to a tweeter using a capacitor. So you can now imagine what happens. A capacitor is a short circuit at high frequency. So as the frequency increases, the impedance of the capacitor drops and the current goes on increasing. Remember, at high frequency, here impedance increases, here impedance drops, and most of the current flows through the capacitor. At low frequency, here impedance decreases, capacitor is almost an open circuit, and no current flows through the tweeter. So that's how the current flow happens. You can divide it into two parts. So this is, and then some cutoff tweeter can be applied over here, and this is how overlap will take place. So this is a simple circuit, but modern day circuits can be complex. Then software is also there, which I'm going to talk about it in a while. Loudspeaker efficiency as usual is defined by output power divided by the input power. That's the standard way to define efficiency. Most of the loudspeakers are very poorly efficient. Their efficiency is very poor. A lot of energy is wasted in the form of heat generation in the magnet and the coil system, movement system. Very less amount of energy is transmitted in the form of sound output. It all efficiency depends on the magnetic strength, cone area, type of enclosure, resistance of the coil, mass of the cone and the coil primarily, mass of the cone and coil primarily determine the efficiency. Although the two most important terms are the magnetic field and cone diameter. So larger the magnetic field, more will be the efficiency. Larger the cone diameter, more will be the efficiency. It's anybody's guess that these two should be the reason. Stronger magnetic field will apply larger force on the coil and make it easier to vibrate. so the efficiency will be more. Larger cone diameter produces more sound output, so the efficiency will be more. So it's anybody's guess that E will be dependent on B and D. So they are the most important terms. So that's about loudspeaker efficiency. Loudspeaker distortion. So loudspeaker can produce a lot of distortion. In fact, if you are careful observer, listener, you may find a lot of distortion in the loudspeaker depending upon the kind of music you are listening to. Large diameter cone moving a small range will give you less distortion. That's the thumb rule for distortion. That that if you, think about the reverse. A small diameter moving a large range will give you more distortion. So in fact, that means if you take a small speaker for a given room, if you take a small speaker and if you run it at its full volume, remember the large range means full volume, it will give you more distortion. So that's why whenever you purchase a loudspeaker, you always purchase loudspeaker which is little bit of over capacity, in a sense that, like, if you are if you have a room of certain size, you buy a loudspeaker which can fill the room with a larger size. Now, when you take that loudspeaker and play in your room, which is of a smaller size, then the cone moves a small range, and the distortion will be less. It would sound pleasant. So always buy a speaker which is a size larger than whatever is your room size. The magnet size, voice coil design, and suspension decides the distortion. How do they vibrate? All these designs will produce linearity or non-linearity in the vibrations, and that's how the distortion can come in. Travel of the voice coil beyond uniform magnetic field. Remember, we had spoken F is BIL, that is force acting on the voice coil is a product of magnetic field into current into the length of the voice coil. Then in that case, the traveling of the voice coil when it vibrates, if it goes into non-linear part of magnetic field, only a small part of the magnetic field is linear. Most of the magnetic field is non-linear. So if the voice coil goes beyond the uniform magnetic field, then the non-linearity would be introduced, extra harmonics will occur, and the quality of sound that is coming out from the speaker will get distorted. And there are Doppler effect distortions as well. You know that when the cone vibrates, then it's shown at some time it is source moving towards the observer, at some other time it is source moving away from the observer, and the Doppler effect distortions can come in. One needs to counter that as well. So there are lots of sources of distortion. Most of these distortions are measured in terms of a pure tone. There are many ways to measure the distortion. One simple way is that you you feed. We have not done distortion analysis. Uh, we have done frequency response of a speaker. Distortion analysis are easy to do. You feed the speaker with a given frequency, say 1000 Hz. See what sound it is producing. You record that sound and analyze it through the Audacity. Now, if the Audacity also shows you only peak at 1000 Hz, that means the speaker is faithfully reproducing that sound. But if the Audacity is showing a peak along with 1000 Hz at some other frequencies like 2000, 3000, 5000, etc., that means distortions are creeping in. Other frequency, non-linearity is creeping in. And in that case, you need to figure out that how much is the distortion. The amplitude of the higher harmonics will determine how much is the distortion. So this is one of the simplest way to measure the distortion. Other way is You take a modulated tone, a high frequency tone modulated by a low frequency, feed it to the speaker system, take the output, record it in Audacity, figure out whether you get F plus FC plus FM, FC minus FM, or you get more higher terms. So all these things can be done to study the loudspeaker distortions. So then there could be a crossover frequency sorry mismanagement and an interference because of that. So we have just seen that in multi-speaker system, your some frequencies will go to one set of speaker and some other frequencies will go to other set of speakers. Now if you put if there is a distortion in that frequency management system, some cutoff value has got changed, some register has failed, some resistance has changed because of temperature, etc., then there could be some mismanagement and there could be distortion. There could be some missing frequencies which might be difficult to obtain. So even that can introduce loudspeaker distortion. So you can see that there are many ways to produce loudspeaker distortions, and once you are experienced enough, perhaps you will understand that how loudspeakers distortion can be observed and minimized. Now the one more topic, and that is of earphone or headphone, and that I will leave you for the self-study. Well, please, it's a small topic in the reference book. Please do it on your own. A lot of discussions are similar and related, so I'm not doing here. It will be there for the exam. So please do it on your own. Don't skip it. So going ahead, what are the newer technologies? So present day, modern day loudspeaker technology is fairly modern compared to what we have spoken so far. Our reference that we are using, Rossing and Woods, does Moore, does not go beyond 1980s, 1990s, maybe early 2000. Lot of newer technologies have arrived which are much advanced. We don't have a need to get into the details because this course is really all about the fundamentals of acoustics, not the very advanced things, but we should at least be aware of it. One of the things that has come is the wireless audio. So now you know, you're all familiar with that. Bluetooth is the common name, but there could be other systems as well. So the audio is wireless, that is from one particular one device to other device, the audio is transferred in a wireless manner, and therefore there could be distortions regarding the wireless connections. There could be the delays uh, according to the regarding the wireless connections, everything. So one has to be very careful with that. The other kind of thing that the speakers have learned these days are spatial awareness and people around them. So most of the speakers, what they do is they employ the use of multiple microphones. Microphones, which we are going to talk about in the next class, they use speakers use microphones to generate a sound, or whatever sound is generated, it will be reflected from the walls, ceilings and the floor on all sides. The microphone will sense it. Microphone will determine that how far is this wall, how far is the front wall, how far is the side wall, how far is the ceiling, how far is the floor, and with that algorithm determines where is the speakers placed in the room, and then accordingly the speakers will modulate the sound output. So in some cases the sound output can be uh, some speakers can fire first, some speakers can be delayed to give you the surround sound from any place. Also, the speakers these days have microphones to sense the voice, and and act on the basis of the voice. Examples are Alexa and others, as you are familiar. So the spatial awareness is the new thing that the speakers have learned. 360-degree surround, especially in the case of headphones, you will get 360-degree awareness, so that, for example, if some music is playing in the right ear, if you turn by 180-degree, the same music will play in the left ear. So you are turning by 180-degree. The system senses that you are turning your head, and it shifts the music to the other head. How they achieve this, I'm going to present some fundamental experimentation on this, maybe a 2 chapter later, not now. So 360 degrees surround is there. Spelling correction needs to be there. Noise cancellation again is the new thing. Again, I'm going to talk about it in a bit, in small detail, when we do the chapter of noise. But you know that the noise cancellation headphones are very expensive. Presently, they are the in things by which you press a button and you all an external noise is shielded. So these are the newer technologies which are there today, and our speaker design is modifying quickly. Let's check some of the problems. What are the advantages or disadvantages of air suspension loudspeakers? So we have already talked about it. Advantages and disadvantages of air suspension, that is loudspeaker in the box. So we have seen that the air suspension is large, the air is a soft wall, and the back wave is eliminated completely. If the box is small, then the air hit back hard and the sound production improves. You can have a vent also, that also gives the output. So we have discussed that in detail. How can you get a good bass response from tiny loudspeakers? Yes, there I'm going to talk about a little bit. Remember, the tiny loudspeakers, definitely they do not produce good bass or good bass. So in order to improve it, there are many things which can be done. So for example, one way to a company does it, that it has placed its speaker in such a way that it fires all the sound energy towards the bottom side, that is on the surface on which the speaker is kept. The say, on a table, the table surface becomes the part of the speaker and produces a better bass effect. Similarly, some speakers are designed to be kept in the corner of a room, so they take the help of the two walls to create a greater depth in low frequency production. Now, present day, one more new thing which has come is the audio signal analysis, in which most of the frequencies are now Fourier analyzed. So we don't use low pass filter, high pass filter, band pass filter circuits, but we Fourier analyze the frequencies. We can then, once we know what frequencies are present, then we can amplify the low frequencies or amplify the lower frequencies digitally, fed it to a speaker, and produce a good bass effect. So there are many ways to do it now. It's a very interesting science and growing rapidly. Compare the cone areas of the speakers having diameters of 20 centimeters, 30 centimeters, 38. These are the standard cone area, cone diameters. Remember, the cone diameters and cone areas, uh, cross section area affect the sound output. So that is why the problem is there. It's a very straightforward question. Diameter is given, radius can be found, and area is pi r square. So once you do that, you will get those three areas, and then you can compare them in the ratio like 1 is to 2 is to 3 or something like that. So you can do that and try to get the answer. Although if you are wise, you can get the answer straight away, 8, 12, 15. So roughly in the table of 3. Sorry. For a satisfactory operation down to a cutoff frequency Fc, A horn loudspeaker should have a mouth diameter at least 1/4 of the wavelength of FC. These are the design considerations of a horn loudspeaker. Its diameter should double no more rapidly than every 1/9 of the wavelength at FC. That means 1/9 of the wavelength, if it's a cone, remember, so it will go from narrow end to the broad end. So at every lambda by 9, the diameter should get doubled. Determine the mouth diameter and the total length of the horn speaker with cutoff frequency 100 Hz if the throat diameter is 5.4 centimeter. So this is one problem you can try to attempt right now and send me the answers. Fairly straightforward, although a horn loudspeaker should have a mouth diameter at least 1/4 of the wavelength at FC. So you have to figure out the wavelength at FC. Sound speed can be taken as 330 or 340 meter per second, and FC is given as 100 Hertz. So lambda is V by FC. So 340 by 100. 340 by 100 is 3.4. So lambda is 3.4 meter, remember. So if lambda is 3.4 meter, then the mouth diameter should be 1/4 of the wavelength as FC. So the mouth diameter should be 1/4 of the wavelength. So lambda is 3.4 meter. 1/4 of that. So 3.4 divided by 1/4 will give you 0.8 something, 0.8 meter, which is around 80 centimeters. So fairly large mouth diameter. And its diameter should double no more rapidly than 1/9 of the wavelength at FC. So along the axis of the cone, if you go at lambda, if you move a distance of lambda by 9 from the throat, that is from the narrow end, then the diameter should double at the max. So diameter is 5.4 and the cone is, the wavelength is 3.4. 3.4 divided by 9 will give you roughly 0.4. So if you move on the axis by 0.4 centimeter, then 0.4 meter, that is around 40 centimeter, then 5.4 should become around 10.8 centimeter. That's how the design will, you can mark these points, and then that is how the cone can be designed. So this is how the design considerations of the horn loudspeaker can be placed in, and you can get a design. A certain loudspeaker has a compliance. Compliance is given 8.7 into 10 power minus 4 meter per Newton. Remember, compliance is 1 over stiffness, K. Mass is given. Figure out its resonance frequency. So we have already seen the resonance frequency. C is equal to 2 pi root K by M, or 2 pi upon root M into compliance, that is C. So you can put the value and get the answer. Yes, Namishka, thank you for that value. So compliance is easy to calculate. An 8 ohm loudspeaker is capable of 30 watt of audio power. So let's check this one. 8 ohms loudspeaker, so resistance is given. It is capable of 30 watt. So how much maximum current can it take? That is what you have to think. So power is V into I, but in terms of resistance is normally written as I square R. So it will be, maximum current that it can handle is root of 30 by 8. You can calculate and let me know how much is the maximum current. So that will be the answer to this part. What much current or how much current will flow when it is receiving 30 watt of power? What size of fuse or circuit breaker should be used to protect it from the overload? So what size of fuse? Okay, and then you require some fuse wire characteristics. Its length, it is asked hopefully. Perhaps you need to check the data sheet must be given. This problem is taken from the reference book. So please check the data sheet to figure it out that what could be the size of the, remember the resistance of the fuse wire should be such that it should not allow the current to flow more than root of 30 by 8. Sorry, yeah, root of 30 by 8. So that is to provide it from the, protect it from the overload. So can we have finished this chapter completely, loudspeaker. We are going to move to the next chapter in the next class. Thank you.